Welcome to Pomodoro Joe for Sunday, March 26th, 2023. Today we're doing LeetCode problem 2360, longest cycle in a graph. This is a hard problem. You're given a directed graph of n nodes numbered from 0 to n minus 1, where each node has at most one outgoing edge. The graph is represented with a given zero-indexed array edges of size n, indicating that there is a directed edge from node I to the node at edges I. If there is no outgoing edge from node I, then edges index I will equal -1. Return the length of the longest cycle in the graph. If no cycle exists, return -1. A cycle is a path that starts and ends with the same node. Okay, so this seems pretty straightforward. We have some graph. Every node in the graph has at most one outgoing edge. If we ever reach an edge that's -1, the graph ends. Otherwise, we're looking for cycles. And looking at this diagram here, we can see that we can have multiple nodes that point to the same node, but any given node can only point to one other node. And that's why we have this array edges that's just got one value. So the index is the node that you're at, and the value will be the node that you can go to. So here we'd have index 3 would say 2. Let's see if that's right. 0, 1, 2, 3. Yep, it says 2. Okay, now that's key. Because there's only one outgoing edge, it means that there are no branches in this path. So this means that once you choose a node, the path is predetermined. There's only one path available to you at this point. Looks like there are two options though for how that path can end. That path can either be a cycle, or the path can lead to a dead end. Looks like it returns -1. Let's see. Yeah, so here, like this path leads to a dead end. So for any given node, we either have a cycle or a dead end. All right, so I think I'll break this down into some sub-problems. The first problem will be, given a node, is there a cycle or not? If there is a cycle, then we'll figure out how long that cycle is. All right, so let's put 25 minutes on the Pomodoro timer and get started. So we'll start with some result, and our result will default to -1 because that's what we should return if we don't find a cycle. At the end, we'll return our result. Now I think, as I mentioned, I'll just go through every node, check to see if there's a cycle. If there is a cycle, then we'll find the length and we'll update our result. So let's see, for every node in, we don't have a list of nodes, but we do know that there are n nodes, and this goes from 0 to n minus 1, and edges is of size n. So we can give ourselves our n node here by getting the length of edges. Okay, so we know our n. So for every node in range n, so range n will give us from 0 to n minus 1. So that's going to be our start node. Maybe I'll call this start node. For every start node in range n minus 1, we'll say, let's see, our cycle will be, let's see, we need to create some function here. So cycle for node, and we'll pass in the start node. Then if there is a cycle, so let's see, if we have a cycle, we need to get the length. So let's see, our cycle length will equal, let's see, cycle length for node. And again, we'll pass in our start node. Yeah. All right. And then here, let's see, once we have the length, we'll just say our result is equal to the maximum of either our result or this new cycle length. So that gives us our basic outline. For every node in our graph, we'll just check if there's a cycle. If there is a cycle, we'll get its length, and then we'll update our result. Okay, now we just need to figure out how these functions work. All right, so cycle for node, let's define that here. It's going to take in some, well, I'll call it start node, I guess. Okay, so it's going to pass our start node. So we'll set our current node equal to our start node. So now we just need to go through our graph. So let's see, while our node doesn't equal -1, then let's see, our next node will be the edges for this node. Yep, so This isn't going to be the most efficient way to write this code. It's just for example purposes to start. Once we get this written and we have a working algorithm, I'll go back and clean up the inefficiencies. Okay, so our next node will be the edges at our current node, and then we advance our node to be our next node. So we move along our graph. Now this works great if we're going down a path that leads to a dead end, but what happens if we get to a cycle? Well, then this will never end. This loop will go on forever. So we need to find a way to figure out if we've reached a cycle. So how do we know we are in a cycle? Let's see. Well, if we see the same node multiple times, then we know we're in a cycle. So let's just keep track of all the nodes that we've seen. And if we see the same node again, we know we've reached a cycle. So let's see our seen nodes. We'll just keep a set. A set will just hold on to all the unique nodes that we've already seen. All right, so while the node isn't -1 and the node is not in our seen set, then let's see. Well, now we've seen the nodes. We better add it to our seen nodes. Okay, I think this works. So we have a start node. We'll start our node at the start node. Then while our node isn't at a dead end, or while we haven't seen this node before, we'll add this node to our seen nodes, and then we'll move to the next node. All right, and at the very end, what do we return? So we could return a true or false. I mean, that's how we're using it down here. But it's actually more useful if we return, let's see, if we return -1, if our node is -1, that would be useful. Then we know there's no cycle. If we return the node that we're at, that would also be useful, because the node that we're at is the start and end of the cycle. So knowing where the cycle starts and ends is very useful. Now, of course, cycles don't really start and end at a particular node, but this is the first node that we've detected that's in a cycle, so we can consider this the start or end. So we'll just return our node. But that means we need to update this down here a little bit. So it's not just saying if we have a cycle. We're going to say if our cycle start node. So now we get a cycle start node. So if that's not equal to -1, then we'll find the length. And we can actually say we'll find the length starting from our cycle start node. So we're not going to start from our start node anymore. We'll start from the cycle start. So if we look at our example here, if we start from our start node, we would start from 0, and we would have to traverse this whole thing over again. But if we start from our known first cycle start, which would be 3, then we can just determine our cycle length without having these extra sort of leading tails. I don't know what you'd call these. These leading nodes that lead up to our cycle. Okay, so let's do this. Let's clean this up. This is too wordy for me, so let's call this just cycle start. Okay, so for every start node, we're going to check to see if there's a cycle. If we have a cycle, meaning it's not -1, then we'll get the length and we'll update our result. Now we still need to calculate our length here, so we have to have some function. Let's call this cycle length for node, and we'll pass in our start node. This is going to be very similar to our cycle for node. So our node will start as the start node. And we already know that this is a cycle, so we don't need to look for the -1. We just need to see if we've seen this node already. So let's see. We need to keep track of our seen nodes. And while our node is not in the seen node, we'll add the node to the seen nodes. All right, so this looks very, very similar. So that's one place we can probably optimize later, since these look almost identical. Now the difference here is we need to keep track of some count, and we will return that count, because we need to know how many nodes are in this cycle. So we'll start with some count here, set it to 0, and then we'll increment our count in here. Okay, so this looks pretty good. So we'll go through all our nodes, finding cycles. If we find a cycle, we'll find its length by counting how many nodes are in that cycle, and we'll update our result. I think this should work. Let's give it a shot. Okay, that works. Let's see if we can pass all the tests. Now, I can almost guarantee we won't, but let's see if we do. Okay, time limit exceeded. So we passed 63 out of 76 test cases, which means that our algorithm works. It's just too slow. So how do we speed up our algorithm? Well, let's see here. One thing I'm going to do, actually, I'm going to copy this test case. I'll go back to our own test cases, and I'm going to add this test case. Okay, so now we have our own test case that matches the one that we ran out of time trying to run. So let's see if we can run this just as our test cases. And time limit exceeded. Okay, that's what we expected. So how do we fix this? All right, let me see here. Can I drop this? Yeah, let's drop that down a little bit. So one thing I pointed out already is this cycle length for node and the cycle for node look nearly identical. Now, what happens when we go through, we have to traverse this entire cycle. Once we've traversed the entire cycle, then we traverse the entire cycle again here. That's going to cost us. So we're doing twice the amount of work. We're traversing the same cycle twice. If there's some way that we can keep track of the length in this cycle or in this loop, then we wouldn't have to do this separate loop down here. So that's one thing. The other thing is for every node that's in our cycle, we're going through every single start node. For every node that's in this cycle, we are going to be finding that cycle again and again and again. So if we start at, say, in this example here, we start at node 0. It's going to go to node 3, and it will determine this cycle. So we're going to start at node 3 and say, okay, we've got that cycle. Then we're going to go to node 1. It's going to go to node 3 and have a cycle. That's the second time we've found the same cycle. Then we'll go to node 2, and we find the cycle. That's the third time. And then 3 and 4. So we're finding the same cycle multiple times. So it'd be nice if we could keep track of which nodes that we visited even along the way of finding our cycle. That way, when we get to our loop down here, we won't be running that same cycle again. So for example, if we start at 0, we go to 3, 2, 4. We can actually flag 3, 2, and 4 as nodes that we've already traversed. We don't need to do this again. Then we'll go to node 1. Of course, we haven't traversed node 1 yet, so we still have to run the cycle again. But once we get to 3, we can say we've already run this before. Maybe we could cache out the value for these cycles. So there's a lot of places that we can improve. Let's just break this down and start at the simplest ones first. All right, so the simplest one here is this while loop and this while loop look exactly the same. The count is the only difference. So what if we kept track of the count in this one? Would that work? Let's see. Let's have some count. We'll set it to 0, and then we'll do the count plus 1 here. But then where do we return this count? So that's not quite going to do it. All right, so if we kept track of the count in our initial cycle for node, this will tell us where we are in this particular cycle. But this has some lead in. Like, for example, when we have 0, we'll go from 0 to 3 to 2 to 4. So this node will get counted in our count, which we don't want because it's not actually part of our cycle. So this count isn't exactly the same as this count. We're starting at a different node. All right, so now instead of keeping a set of our scene nodes, what if we kept track of what count we were at when we saw this node? So let's see, if we start at 0, we go to 1, 2, 3, 4. This was 1 when we first found it. Now we're at count 4. 4 minus 1 is 3. That does look like it might give us the right answer. So if we keep track of where did we see this node, we can eliminate all of the, I guess, leading up nodes that lead up to our cycle start. So let's keep track of, instead of seen nodes, let's keep track of where we saw the node. Let's see, how do we do this? Well, we can keep a dictionary of our scene nodes. And instead of having this add, we'll just say our scene node at this node is equal to our count. Okay, so that gets us a little bit of the way there. So now if we do end up with a cycle, how do we figure out how long that cycle is? Well, it looks like we're going to take our current count and we're going to subtract our scene node at that count. All right, so let's see. How about now we can't just return node anymore. Now we're going to be returning our cycle length. So this is actually not just returning whether or not we have a cycle, it's going to be returning our cycle length. So that looks a lot like this one now. Okay, let's get rid of this. We don't need this anymore. Now we're returning the cycle length directly. All right, but that does mean we have to calculate the cycle length here. So if our node is equal to -1, well, we're still going to return -1. Otherwise, we need to calculate our cycle length. Let's see. Well, the cycle length is going to be our current count minus our scene nodes at, let's see, at the node. So that's going to be our current count minus where did we first see this node that we're cycling on. Okay, I think that should work. So now down here, instead of saying if we get a -1 and calculate the cycle length, this is the cycle length. And so if our cycle length is not equal to -1, then we can just get rid of all this. Well, that cleans up the code quite a bit. And this is going to be cycle length. Okay, let's see if this works. Oh, we still run out of time. Didn't get a wrong answer though. Let's see here. Let me grab this test case. Okay, so our algorithm still works. We've merged our cycle length and our cycle detection into one by keeping this count. But we're still running out of time. So if I put back this test case, we'll see that we run out of time. All right, well, we've eliminated one of our inefficiencies, and that was basically calculating the cycle once to find it and then calculating the length as a separate function. Now, we haven't eliminated the second inefficiency, which is if we've already seen, say, node 3, if we've already gone through node 2, we've gone 2, 3, 4, or 2, 4, 3, then we'll go to node 3 and we'll find the same cycle, and we go to node 4 and we find the same cycle. So down here, we want to keep track of whether or not we've already found a cycle for this node. So when we go from 0, we'll say, yeah, we haven't found a cycle for 0 yet because it's our first node. Then we go to 1. We might not have found the cycle yet for 1, but once we hit 3, we'll say, yes, we've got a cycle for 3 already. So we can just exit out and say the cycle for 3 is length 3. So let's eliminate some of these inefficiencies in here. Well, let's see. We can keep track of nodes that we've seen already. So let's try that. We've already got this scene nodes in here, but we need this to be global. We need to have scene nodes out here somewhere. So let's put scene nodes out here. Let's move this. All right. Now our scene nodes is global in terms of this function. Once we see a node, it's going to be seen. We won't traverse it again. That's great. But will that solve all of our issues? I think there's still a problem here. Because this count starts at 0. If we've seen the node before, let's say it's 10. Well, actually, let's see. Will this work? No, this won't work. If we've seen our node already, then we'll be saying 0 minus whatever's at this node. That's not going to help us because that's going to be a negative number. So this count, I think we need to keep track of the count outside here as well. And if in that case, we need to use non-local count. Non-local? Non-local count. So we have a global count in addition to our global scene nodes. Okay, so now we have a global count in addition to our global scene nodes. That means this count will be sort of universal count, and it does mean that our count will always be greater than some scene nodes here, which is good. Now, if we've already seen our scene nodes before, I don't think we can just do count minus our scene nodes, because this won't be updating, which means that if we come across the same cycle again and again and again, this will keep growing bigger and bigger and bigger. So as soon as we hit this while loop, this node is in our scene nodes globally. So if we've already seen this, let's say, several tests back, then this number will be very big, this count minus our scene nodes. So I think we need to say, well, where are we starting our cycle here? So we need to keep track of where we start our cycle, or I'll call it start count. And that's going to equal the count where we're starting. This is getting tricky. Well, let's just try this. We've made these two global. We have some count. We have some scene nodes. If we've already seen the node, we're going to break out. We don't necessarily want this. I think that is still a problem. Yes, we do need this start. So if this scene nodes is less than where we're starting, oh, then how does that work? So it definitely is good to move the scene nodes out here. So that way we don't traverse the same nodes multiple times. Also helps to keep the count as a global count so that we can keep incrementing and going higher and higher and higher. Let's see, but when we get to a point where we've seen a node, oh, you know, it doesn't matter. So if we see a node for the second time, if we've already seen a node before, then means if we saw that node before, we've already got the loop that it's in, if it is in a loop. So we don't need to calculate this loop again. We can just exit out. So let's see. Though I think that means we do need to keep track of our start though. Because if we just exit out, this count minus this will be very, very big. So we need to keep track of where do we start looking for this cycle. So our start count will equal to our count to begin with. Then down here, oh, and it's time to take a break. All right, I'll be back in 5. Just kidding. Here we go. We'll just keep going. We're almost done. If we've already seen this node, so if we haven't seen this node before, then we need to calculate or find whether or not it's a loop or leads to a dead end. So is this a cycle or a dead end? If we've seen this node already, then it's either already been calculated as a cycle or a dead end. Either way, we can ignore this because we've already seen this node. We've already calculated the cycle or dead end. We can just move on. So if that's the case, if we've already seen this node, so if we haven't seen the node, or sorry, if we haven't calculated this cycle before, then we need to return this cycle's length. If we've seen this cycle before, it means that this scene node will be less than our current start count. So if our scene nodes at this node is less than our start count, we'll just return -1. It doesn't really matter. Okay, let's try this. Oh, and we pass, even our long test case. Let's submit that and see how we do. And we pass, and we do all right. We beat 65% for runtime and 82% for memory. That is not bad at all. All right, let's see if we can clean this up a little bit. So this code basically says we're going through, well, let's break this down again. So for every start node in our range, we'll get the cycle length by calling this cycle length for a node. If that cycle length is not equal -1, then we'll calculate our max result here. But we actually don't need to worry about if it's not -1. Because if it is -1, it'll still be less than our current max, less than or equal to our current max. So let's do that. Does that save us anything? Okay, so that still works. So that eliminates one conditional, not a big deal. It actually might be faster to, let's see, oftentimes it's faster to say result is equal to result if result is greater than our cycle length, else cycle length. So that's one optimization. Sometimes calling max, because it's a function call, will take more time. This does the exact same thing. All right, what else can we do here? Well, one thing, I've got this node, and I set this node equal to next and next node. We can just eliminate this little next node thing here. We don't need this next node anymore. Get rid of that. That might save us a little bit. Okay, the other thing that we're doing is we're keeping a dictionary of seen nodes. We could just keep, so this dictionary is storing where we saw the node, the count where we saw the node. We could just set this to 0. We could make this an array, say 0 of length n. And then instead of saying nodes not in seen node, if we just say if seen nodes at our node is not equal to 0, or no, is equal to 0. So if we haven't seen this node, it'll be equal to 0. Otherwise, we set it to the count, which means that we probably want to start our count at 1. All right, that cleans us up quite a bit. Let's see if that still works. Still works. Let's see if it gets us any kind of gains in our speed. And it does. That's significant. We are now beating 90.97% for runtime and 98.39% for memory. I'd call that a win. All right, so check this one out. This one's super fun. It's 2360, longest cycle in a graph. So we had a couple submissions, one time limit exceeded, but our final submission beats 90% of other solutions for runtime and 96% for memory. That's not bad at all. All right, check this one out. Hope you enjoyed this. Hope you learned something. Hope you can go out and write better code.